Okay, so hi all, nice to see you all come for the workshop. And I mean, we wish we had more people, but it's okay. But good that some of you consistently came for all 3 days. So yeah, so for today's workshop, mainly we'll be covering a bit more of an advanced concept called advanced transformers. And to give you an idea, it's like kind of going into the behind the scenes of how ChatGPT is performed. But it's quite on like the surface level, so don't expect too much. But I would say it will be quite a new experience for those who have not encountered this before. So before we actually get into advanced transformers, it's important that we cover a concept called large language models first. In short, we can call it LLMs, if you want to know. So what are LLMs? Okay, so to give you like a simple analogy, right? It's kind of like your AI version of your like you can call it a superhero like Hyperion or whatever terminology you want to coin it. So yeah, something like that. Basically, it's like a highly sophisticated AI system. And you guys ever heard of ChatGPT? Yeah, definitely. Obviously, it is. Hey, stop shaking. But yeah, basically, it's something like that. So whatever question you throw or anything based like that's relevant to the subject that model has been trained on, it will be able to answer regardless of how you phrase the question. So that's kind of it. Like it will be trained quite a lot. So yeah, why is it called large exactly? So that's where I'm coming to. Like if you guys remember what I said on like day one, like large basically usually refers to things that like models that have very deep neural networks. So there are a lot of interconnected nodes and so on. So, and one more thing to note is that they are trained on vast amount of data sets. And these data sets usually contain quite a lot of words. And since we have moved further on, like it's already day three, I think it's good that if you learn some data science terminologies. So one thing for y'all to take note of, right? In data science, they want to make things a bit complicated. I know, right? So instead of calling it just word, right, they're gonna call it word corpus. So there's a lot of word corpus in there's a large amount of word corpus in a data set like for all those data sets that are used to train all these LLMs. So okay, how are these large language models like develop? What is the so-called life cycle for this? Usually it's like quite simple. If you guys have machine learning like knowledge and so on, this is like the basic steps of how it works. First, you get the data. Data will always not be what you expect it to be. It's gonna be in a clutter of mess. So in order to get it to be in the way you want it, you have to clean it and you have to prepare the data. So that's the first step: data ingestion and preparation. Then going on, you have to build the transformer model. So what are the requirements you want it to do? What are functionalities and so on. Then you do some pre-training. Then the pre-training you find, oh, this doesn't work. Then you go on to fine tune it, and then you actually go on to evaluate the model, which is like the model accuracy and all, training accuracy. Then when you put it on test data that it has not seen before, it has to be good and so on. So that's where the evaluation. Then finally, when you think it's good enough to go, then you deploy the model. So yeah, this is like a basic steps. Honestly, this is quite similar to what you see for general machine learning, like modeling. This is how developmental stages look like. Okay, so now that I mentioned large language models, okay, one thing I already said, one of the most popular large language models that all of you know by now, you're lying if you don't know, man. All of you use it for your work, and that's your GPT. And if you didn't know till today what the full form is, it's actually called Generative Pre-trained Transformer, and it uses the transformer architecture. Oh, remember that it's quite important. And the things that GPT can do, if you're not aware of, is text generation, language translation, sentiment analysis. And to give you like a brief teaser of what it is, sentiment analysis is like basically like trying to identify the tone that is largely used in a particular text. So if let's say I'm trying to examine the emotion you're trying to convey through a WhatsApp message, then it will try to look at the words you use and try to figure out the so-called emotion that this message was trying to convey. Then finally, question answering. Yeah, all if you use it for that. So yeah, no point. Finally, other than GPT, there's also one more thing called bidirectional encoder representations from transformers, and that's in short called. But definitely, I think most of you wouldn't have heard about this before, unless you have prior experience. But yeah, basically, yeah, again, take note, it uses transformer architecture, and information that it processes is like in bidirectional. And you want to see if you notice something, there's a similarity between both like large language models covered. Both use transformer architecture. Oh my days, that means oh my god, shock of your life. Next is gonna be transformer theory. Let's go, and Hui Sang gonna cover it from here on. So thank you.
All right, thank you, Karthik. So I'm going to screen share now. So yeah, so now we'll be moving on to transformer theory. So as you may or may not know, a transformer consists of like a very, very deep architecture. And the reason for this is, it's able to do many, many amazing things, like some of the examples mentioned by Karthik. It can answer questions, analyze for sentimental analysis, and many much more. So, because it has such a deep architecture, there's a lot of like computation required. We try to minimize the amount of like things you have to remember and try to simplify it as much as possible. And as much as possible, we try to relate to real life examples so you're able to process the information much more easier and yeah, etc. But basically, you can think of Transformer as like a deep learning architecture that can be utilized for text processing, understanding, and lastly, generation. So yeah, this is like pretty much an architecture that was proposed in order to be an upgraded version of the RNN architecture, which I'll explain more later on. So Transformers was first proposed in a research paper called Attention is All You Need by Dr. Vaswani and his team of researchers. So as you may pay attention to the title over here, like attention is all you need, there's quite a bit of an emphasis on the word attention. So let me just quickly go through what I said. So because the transformer architecture, it relies heavily on a component called attention mechanism or self attention, which later on my friend Samuel will go later in depth into about. But just take note that it is quite a big part of the Transformers architecture, and it pretty much helps the more to know what certain words means in like based on its position in the sentence and the words around it and etc. So, like, if you remember what I said previously, it was proposed to be an upgraded version of the RNN architecture. So, let me just quickly go through what I said. So firstly, as you may or may not know, like, in order to do like large scale like text translation and etc. into the model, a huge amount of like data processing is needed. Like, you have to feed the words into the model and etc. And because RNN doesn't really take advantage of parallel computation and that makes the whole process much, much slower. Whereas transformers, it takes advantage of something called like cells or units. You can just call it that for now. And it's able to duplicate it in order to take advantage of computational processing in the sense that it's able to process multiple key component words within a sentence at the same time. So it's able to make the whole, training process much, much more faster and it makes it so much better, yeah, basically. So moving on from that. So yeah, I know it sounds quite a bit to like take in, but it's really not that bad. The way you can think of it is, just adding numbers onto one another. So let me just quickly go through like some of the simple foundation steps when it comes to the transformer architecture. So to begin, as you or may not know, whenever you try to feed data into any model, like it doesn't matter what kind of model it is, like even the most simple model, like the um, the linear regression, etc., you all have to feed it in the form of numbers. So it's the same thing for text generation models like the architecture model or anything else that my friend Kate has mentioned, like the GPT or but you always have to translate the inputs and outputs to words so that it's able I mean into numbers so that it is able to find the correlation and be able to do the modeling properly. And that's where the encoder and decoder comes in. So the first thing you do is, you have a string of text. So let's say I'm trying to create a model that's trying to translate the English language to the French language, right? So the first thing that the model has to do is translate the English language into numbers or process it into numbers. And it has like a large number of components within it in order to do so. So as you can see the multi-hit attention over here, it consists of like a large number of things. So let me just give you some examples of what it contains. So it contains things like word embedding and also things like positional encoding, self-attention, again, a big portion of it, or what's the thing called? The attention mechanism, like it's a synonym for it, and then residual collection, and yeah. So all these numbers, you can just think of it as like a way to convert the words into numbers based on not just the words, but the positioning of the words, and also the value it carries around based on its surrounding words. And lastly, a final like number that connects all like the value behind the three processes that I mentioned before. So yeah, yeah. Again, this sounds really complicated, but you can just think of it as numbers being added onto one another to generate a final number that contains like a true value to it, which can be useful to the model. And once you have like generated like these numbers for the input, you can then do the same for the targeted or the expected output. So now that you have these two numbers, right, and that's where like the key important part of the decoder comes in, where it tries to find the relationship between the expected input numbers and the expected output numbers. And it's through this like relationship it's able to generalize basically somewhat of a prediction, and that way it will be able to know like what words within the English language would be able to translate into the French language accurately. So, yeah. So I know that sounds a lot to take in, but as much as possible, I try to simplify it. And if you're more interested in it, you can just look online or see some YouTube videos to learn more about it. But yeah, but do take note, it's quite a heavy concept to take on. Yeah. So now moving on. So now I'll try to use a real life example. So as you can see from info over here, the guy, he asked the question, how do you implement like efficient bubble sort, right? Then afterwards, the encoder would try to process the input and such that, it is able to like be utilized for the prediction. Then that's where afterwards the decoder comes in. So if you remember what I said previously, it tries to find a relationship between expected output and the input. And then this is where you say, oh, I know the answer because I know the relationship. And then from there, it's able to propose an answer for you, which is, just search Stack Overflow on how to implement the effective algorithm and etc. So yeah, now I'll move on to like the simple things of what the transformers are made of. So is if you can remember what I mentioned just now, it consists of things such as the encoder, decoder, and also the attention mechanism. So yeah. Now moving on to encoders. So Samuel will take over this part for me.
Firstly, we'll have 15 minutes of break time. So we'll be back for encoders mechanism at around 10:45. So meanwhile, you could get a drink, or you could sit down and process the information. There's not quite a lot covered, so you'll be back around 10:45. So meanwhile, I will share my screen and play some music.
I made a little bit of money. I paid this cover. I ain't gonna stand still. Cause now I'm finna wah. Now let me see you wah. If they let me get lost, if you don't, look at the reaction when I hit them with the phone. Got Fleazy in the back, got cello in the front. Listen to the record, boy, I got what you want. Bitch so fly, cause the club on chon. Got hits like the wolf is beating the back of the dome. Ladies take it back, throw back the dome. Bend at the waist, lean to the front. Now bounce, shove out to the beat, just a little bit. Pause, show me your feet, just a little bit. Ain't nobody here, why better than me? Purple flag to the left, who better than me? I got a all-star squad, who better than me? Man, listen to the beat, who better than me? I paid to get in, so I ain't finna chill. And my week been way too long to stay still. I paid this cover. I ain't gonna stand still. Cause now I'm finna wah. Now let me see you wah. Dash, why you had to do it like that? Got these ladies taking their back, looking like they breaking their back, taking it back. Wait, now I'm checking shouty with the microwave, hotter than a baby in a microwave. Look at how she whopping, man, she might get paid. She whop a little harder. Look at how she whop, she a party starter. I hope that security remember the Carter, cause I ain't been a whop over two and holler. Said I never drop dime, but I drop me $1. Told her give me a number and maybe I call her. She said that she knew me and she know I'm a baller. Man, I've been a while out of here, I see her tomorrow. I paid this cover.
Hi, so our break is over, so I will continue with the encoders and the decoders of the slide. So if I want to introduce myself, hi, I'm Samuel. So I'm a upcoming year student in data science, so I'll continue on encoders. So next we have encoders, which is a very simple mechanism in transformers where it takes in the input text and it tries to convert it into a format that the model can understand. So it breaks down these input text, right, into smaller parts, which are known as tokens. So remember in lesson 2.1, right? Day 2.1, we actually covered tokenization, which allows to break a sentence into some, like each individual word. So, for example, I am a robot is a sentence, then I is a token, M is a token, as well as a and robot is a token. So we then convert these tokens into numerical vectors, or in this case, they simplify it, they call it index of token K. So they are in a sense assigning the tokens are actually assigned numbers. So because but then in the sense you want to make it more complex in the more zoomed in position, you are doing a numerical vector so that the numerical vectors could represent what the word actually is in just a few numbers, right? So of course there are a lot more to this, but these sum up the essence of encoders. So don't worry about these sine, cosine, the math behind it. So it's just for your own understanding lah. Like you don't really have to like dive too deep into why is there a sine and why is it a cosine. But all you know is just that sine cosine are used to determine its positions in the sequence. For example, like I am a robot, right? So uh, what's the difference between I am a robot and I am robot? So obviously there are different sequence, or even I am robot right, there are different meanings. So in that case the robot, right, in this sequence, in this position will have its own position encoding value, as well as when it swaps its position, like I am robot the robot in another position will have another positional encoded value. So take note that when different positions, it will have different kind of results. There are different contexts. So when we swaps, it has different contexts. So moving on, we have what they do. So I always call encoders as smart translators, and they are taking sequences of information, and then they understand what each word means. They look at relationships between them, known as self-attention. So self-attention, you covered that in 2.1, right? It's basically the importance, the weightage of every word corresponding to its other words. So the weightage itself is how important the word is in the probability context, right? And then it's shown by turning words into numbers or vectors. So since the model only knows numbers, we could only put them from these words into numbers that are suitable for this model to understand, because they only understand numbers. So moving on, you have word embeddings. What do I mean by turning words into numbers? Right. So we learned this in day 2.1, whereby we discovered same concept. So understand how transformers and the same concept, seg to seg models, they literally kind of do the same thing. Okay. So at 2 dimensions, we represent words like uh man and woman. So I'll give this example again. So gender 1 and gender 9, right? It shows the polar opposites of the genders. So for example, like, okay, I know that there can be more than 2 genders, but let's only stop at 2 genders for now, which is man and woman. Okay, let's not go into that. You will not, although we are aware that there are more than 2 genders. So men and women are 1 and 9 respectively, and hence uh they are actually put in the opposites, and as well as even grandfather and boy are put in opposites, because assuming a boy is 20 years old and a grandfather is 90 years old, right? Then you just have like a big contrast, and this is known as like uh, the coordinates of 1,9 and 1,2 respectively. So, so to describe a male, old male, it will be a grandfather. So the coordinates will be like here, and coordinates are here for a young male, as well as a young female and a older female. So this is like 70 years old. So given all these contexts, right, it also learns genetic patterns like adult, child, and infants, very general. As it doesn't really know is gender. Okay, so question is, for coordinates it has never seen before, right? How would it be able to sort of estimate what uh what kind of context it tries to entail? So for example, 10,10, right? I give the example is the 10,10 is like, it's never really seen this before, but you can estimate that 10,10 is a female gender and it's 100 years old of age, and hence it's a grandmother. You see how just using two sets of numbers, x and y axis, we could already describe what a word is without the model even getting to look at it. It's like, let's say it's not look during training, it could always try and guess what it is. Yeah, so that is the essence of 2 dimensions summed up in a nutshell. Okay, but you can ask me that why don't we represent this in a more detailed manner? Because some of the words like in our chat GPT is just uh example is very, it's very general, and hence we call it global vectors. Glove, GLOVE, glove. So global vectors, right, are vectors that have considered many uh context, and it's pre-trained in a way that is trained previously by other developers. So other developers have came up with like 50 dimensions instead of just simply 2 dimensions. It's even like uh name or name kind of axis where it's like A to Z or something. Starts with A to Z, or rather or the salary of a person. You could give multiple variables. So if we extend this more, you could describe one data point even better and even more sharper and clearer, and this is 50 dimensions. But of course, in visualizations, we could only visualize it in 3D. So you could only do like 3D, so X, Y, and Z axis. So for example, we could effectively describe things from a 3D axis known as dimensionality reduction, which is a bit like what we've gone through yesterday, which is Disney. Because sometimes it's hard to visualize 50 dimensions, so we could only visualize 3 dimensions, right? Okay. For example, you could even classify cluster, city, food, and a body part, or travel, or feelings into different clusters in this global vectors, right? And it's able to cluster pretty well. So given this algorithm is able to do this, you can actually sum up meaningful patterns for data analysis, and this is known as exploratory data analysis, right? EDA. So let's move on to the optional how far analytics could go. So we could even cluster data that are related given a theme. So again, like we talked about Disney. So Disney is a dimensionality reduction method. It's to reduce 50 dimensions into just 2 or even 3D dimensions. Basically, it sums up to things that we can plot out because we cannot really plot out four dimensions, right? So we could plot 3. It's easier in a sense. You could see what's going on more. So for non-fiction, we see at a cluster. There's for crime fiction, there's a small cluster, it's a very rare cluster. We could again have very good detailed insights, and this is actually carried out by complex algorithms developed by these researchers over the years. For Disney, we're not going to discover Disney very in depth for now, but all I can say is Disney uses algorithm to group up things. It basically when this is converted, this 15 dimensions is converted to 2 dimensions, right? At first it will be like all over the place. These data points are all over the place, and whatever cluster that you observe we'll just don't have any clusters. It's just very randomized because it's very hard to sum up 50 variables in 2 variables. So what Disney does is that you try and run through a for loop to ensure that these data points that are together will try and be together. Yeah, in the 2 dimensions. So moving on, you don't go into in depth of that. You go through positional encoding instead. So positional encoding are given like word embeddings of how, are, and you, and plus keyword is plus the positional encoding denoted PE of that word, right? So it's only given these two, then we are able to give a matrix for the input sequence in numbers. We are able to describe the input sequence correctly as of how um how these numbers are supposed to be described as for the sentence. So for example, for word embeddings for each word, right? In this case, 4 dimensions, right? 1, 2, 3, 4. 4 boxes in grid. So how are and you plus the positional encoding of that particular word itself. So position encoding tells us in which position is the word. Right? So we discussed like I am a robot and versus I am a robot. Have 2 different meanings. So the positions for both these sentences will be different, and hence this is altered, this is altered, will form a brand new sentence, which is like a brand new kind of set of numbers to represent that. So I hope this gives you understanding on how data processing is ensured to process this data into, well, things that describe and to use for the decoding process. So to continue, kind of this is how it really looks like. But then we won't, you may first see that it's very fanciful notations of sine and cosine, but we don't have to cover what sine and cosine are. You could always refer to its papers to see more, or you could look at StatQuest. I could recommend StatQuest on transformers. That's if you're very interested. I have team members who are new to the concept, but when they look at StatQuest, they are able to digest very quickly. So I strongly recommend you could use StatQuest as the view by Josh Stammer. He explains it very clearly on sine and cosine. Okay, but if you want to learn proving, it's like a whole other syllabus topic. Right. So step 3, attention mechanism to help the model focus on important parts of the input text. So we assign weights to each token. So remember, actually it's not day 1.1. Yeah, day 1.1. But then it also has day 2.1 because attention mechanism is covered in day 2.1. So this indicates the relevance to the current prediction. So similarly, the weights refer to how important the word is. So for example, fruits and fruits, right? Fruits is very important to fruits itself because it describes itself. So self is known as self-attention, and hence by itself it has high importance denoted rate. So in the matrix itself, fruits and R. So fruits, the R would describe fruits, and hence high importance, high attention, slightly high attention, and even deletion as well. Why is deletion important? Because to fruits because delicious describes fruits and hence delicious is a high weightage. However, R and delicious, you may think that R and delicious is like not that important, and you are right because R does not exactly describe delicious. And actually, R is a stop word. So a stop word would not uh describe something very well, even and the, right? You don't need the and the, and you can still make up words. For example, the quick fox, the brown fox jumps quickly. So quick fox jumps quickly versus the quick fox jumps quickly. The will not have much importance, and hence the itself is a lower weightage. As well as delicious, those stop words with R, right? Usually they are like low attention. And you could see again itself high attention, itself is a high attention, and then you try to compare value vector, zooming into this of fruits into a three-dimensional vector and plus fruits and fruits correlation and fruits and R correlation and fruits and delicious correlation in those attention mechanism. So this is gone through position encoding, word embedding, all that. And afterwards, the vectorizes representation for fruits with relevant attention information from the input sequence. So I hope this gives you a very simplified understanding of how the sentences could derive meanings of just of one sentence alone. This is all it's going through. Is generating a very big matrix. For example, if this sentence is very long, right, it will generate a very even bigger matrix. So it's like, whoa, it's full of like, it's like a GitHub commit. GitHub commits are like full of green color, right? Yeah. So that is what we are trying to achieve. We are trying to simplify this same words compact with high importance, the rate. Okay, moving on. So this is a totally optional add normalization and feed-forward neural networks. So it's not covered in syllabus. We just need to know that the numbers are passed through the transformers neural network. So the feed-forward neural networks are just a very atas way to describe a normal a normal transformers neural network. It's just the day 1.1 neural network to train. So yeah, data scientists on the sound atas and all that. So neural network can then understand meaning and structure in the sentences. So moving on is just to putting these vectors, right, to train this transformer's brain to understand what it actually means, not as the feedforward neural network. And then you go to the decoders. So the decoders, I like to give an example. It's like you are trying to, in a sense, interpret ideas into actually insightful insights, like useful answers. So I'm giving this creative writer very meaningful ideas, and then it's just generating ideas based on what I told the creative writer to. It's generating things right now. So it's like decoder, right? So it takes the encoded information, generates output text based on that information, and it uses encoded vectors to predict the next word in a sequence. So to move on to the components of it, it has self-attention layers to help the decoders understand the relationships between the tokens in the input sequence, and feed-forward neural networks process this information from self-attention layers to make predictions on the next tokens in the output. And these two work simultaneously, right, to understand input sequences in numbers to generate meaningful output sequences based on that. So decoders have self-attention layers as well, just like the encoders, like and all that, and they also have straightforward neural networks to process information. So that one is like what we covered just now, lah. So we cover this very simple concept known as masking. So decoder, right, just to know that it trusts, you don't know the specific details, just know that it just decodes things for you, right? So masking is a way to prevent model from cheating. So it ensures that the model is, give me a moment. It ensures the model does not cheat by picking at future words, we call it tokens, during the prediction itself, right? The skill scores are actually, if you think about it, skill scores are just normalization of the add norm and fit for the network. So normalization is a way to scale down the data into just small numbers. Remember that neural networks don't like big numbers. So if our vectors are numbers are too big, we'll try to scale down to just like from 0 to 1, and it's like very simply represented like 0.7, 0.1, like that, right? And then you go to look ahead mask. So look ahead mask has, realize how he has minus infinity. Minus infinity refers to nothing. So anything multiplied by nothing gives you nothing. So again, the matrix works like this. It doesn't multiply row based on by column. So again, it's not like the secondary school E-math. You will think that this plus this actually is, you can say it's like times. It's a bit like times, but they call it plus. So like they want to confuse you. So like, so anything multiplied by infinity is infinity. Negative infinity is undefined. We don't know. The model doesn't know what this value is because it doesn't look forward. You see, as well as all this, right? So it doesn't look forward of I love generative AI, right? It doesn't look forward to love. So I even looks to I, but it doesn't look forward to love, and it tries to predict love. And then when it has I love, it doesn't look forward to generative because infinity is like multiplied by basically undefined. So you will try to guess what the next word is, so you know it's mask scores. So it doesn't cheat lah. So output words. So ever wonder why this ChatGPT generates word by word against time? So output layer simply determines the most probable word given all possible words generated. So for example, for I, right, is 0.7, M is 0.2, and phi is 0.1. Hence, next generated word equals to I. And then it's like generating, ChatGPT generating word by word, word by word, word by word. Yeah, so this is what's going on. Mind blown, right? So this layer is probability calculations of all the words. So imagine this is many words, more than just 1, 2, 3 words. It's like 1, 2, 3, 4, 5, 6, 7, 8 words, right? So from the 8 words, it tries to determine what's the most probable word and outputs that word based on this algorithm known as softmax. Right, so softmax we covered that in day 2.1, and it's a way to output things based on that layer. So we don't have to cover all this. You don't look at all this, but all you need to know is it goes through a few layers of based on this input sequence, and it tries to go through many layers to come up with the answer. So now we move on to model training. So during the model training, we will zoom in into how ChatGPT tries to look into this data. So simply what it does is train using large data sets of text. And during training, the model learns to predict the next word in the sequence given the previous words. So for example, who does bird live with? You will try and give attention to what is being fed. The input data is being fed, like bird lives with Ernie, right? So who does bird live? And then it tries to have Ernie as the highest attention because Ernie describes what bird lives with. And then you try to compare using the attention algorithm. And then it's like Ernie is the answer, hence output Ernie. So who does bird live with? Ernie. Very simple, right? So training transformers, we suppose the question, what is the name of the tower in France? So the actual answer is denoted Y, right? It's the Eiffel Tower. However, the model's answer is denoted Y pred, right? So in statistics, we have like actual answer, actual output Y, predicted output Y pred. So like Y pred is the lower. And since this is not correct, so lower is not correct. It's actually a museum in somewhere else. It's not the name of the tower in France. And hence, since y is not equal to y prep, the actual answer is not equal, not the match that predicted answer that the answer that ChatGPT gives, this transformer gives. The model adjusts how to learn from data, not as model tuning in feed-forward neural network. So the feed-forward neural network will do back propagation, tune, and then this is not covered very in depth, but all you know is that the feed-forward neural network has engineers to tune to understand how to improve this AI model, right? So you try and go through many different tuning graphs. You see a lot of like stock market graphs, and that's how it works because it tries to see the optimum maximum point, known as the local maxima, and then it tries to determine its possible like best hyperparameters based on it. So hyperparameters refer to how model tuning can be optimized. So let's say I want to tune things like learning rate, how fast the model learns. And then if it learns too fast, it's like it goes up, out of hand, right? But if it learns slowly, it just doesn't improve that much, and then it hence takes a longer time to do. So we want to the fastest time, and yet it training in the best, like the best outputs of that model. So it's known as model tuning. So Moving on, we'll have applications of transformers, which are used in various applications known as language translation. So remember day 2.2 on side-to-side models, and also text summarization and question answering, the SIG lessons focus. So question answering, we'll be covering today's lesson, but we won't cover the rest because language translation is only covered on day 2.1 actually. 2.2 is the practical. Text summarization not at all. You can explore it on your own if you want to. Okay, it's another algorithm to do it. And question answering is today's lesson's focus. So we now have pre-trained models with practicals, 20 minutes, and then we will see how early we could end this lesson by. So we'll first do the pre-trained models with practicals. It's 20 minutes. We'll first go to our Google Colab. So for this practical, right, just open our Google Colab. I'll give us like 1 minute for us to do so. Okay, so assuming that you've already logged into Google Colab, we'll try and do a simple exercise. Okay, this first step is entirely optional because we know that Google Colab itself already has a inbuilt transformers library by itself. So we could do a terminal and then we can click install transformers. This is entirely optional, right? But if you want, you could pick install transformers from here and then you can get started. So based on text generation itself, we are the first simple model we're gonna look from pre-train. Let's go. For now, we're gonna code from transformers import pipeline. As well as the generator is actually the pipeline process of it. And then the model, right, is another parameter to specify which model you want to use. In this case, we are using GTP2. It's a simpler model. So the prompt will be once upon a time. As well as response is a generator prompt. And lastly, we want to print the response out. So print response, the first response like response index 0 and its respective generated text. Simple, right? Just a few lines of code that we could use a pre-trained GPT to do the work for us. So now you're trying to load in the config.json as well as this model dancers and the vocabs as well as tokenizers. So it's trying to generate things like this. Next morning, the manager came to us and so look at how just 1, 2, 3, 4, 5 lines of code. It could already generate meaningful responses for this GPT-2 based on a prompt that we give it once upon a time and then continue that story. So once upon a time, the next morning the manager came to get us. Simple. Oh no, once upon a time I was at the first floor. I was at the so that is the next the next paragraph. So apologies. Once upon a time I was at the first floor for a group of students who all took a break from a regular job. I was always there, always in the corner. So I describe the narrative based on the words that's being fed. Then the next morning the manager came to get us. So he's describing working scenario, like a full-time job, a part-time job. And then he just describes a story based on it. Yeah, it's getting creative and tries to link based on this story, right? You just try to link it based on the what is being said. So I said something and then I remember what I said and then I link the next sentence, I link it towards it. So also attention, a bit like attention mechanism. So see how attention mechanism is so beautiful, it's able to capture the semantics, all these semantics and all these assets of GPT is all described by one word called attention. Okay, enough of me talking. So we give it context, generation based on these input prompts. Next one, Q&A. This is the chat GPT already. So like based on what question we ask, it generates a chatbot. It answers things based on it. So just generator equals to. So you can follow my documentation. I'll first add in a text. So this is text generation. Cover the basic use case. So now we cover a basic use case, which is question answering. Okay, so I already made a question already lah. So you could just I'll give you a while because I already have this on my side. I'll just give you a while. I'll let you copy this down. This for around 2 minutes. So by the time 2 minutes we will continue. So you should see things like, oh, you should probably train this model on the training task. It's just to answer overflow. So I give it context and then ask who are you, and it just respond overflow. So I give you 2 minutes to copy this out. So I'm back and I hope you guys have taken this down. So answer overflow. Who are we? We are overflow. We try to determine like the attention, which one is the most like relevant answer, and outputs that are very simple. Context equals prompt, question equals question is like the parameters that is supposed to put into the generator. Answer. Then it's still one is a data pipeline. So I think we covered this before. Data pipeline is like it's like dirty water going in and clean water coming out. But I don't really call this dirty water. It's actually also clean water. So clean water coming, another sort of drinks will come out. Yeah, some drinks will come out. Vanilla flavor maybe. So we'll go through one last practical and then we will end today's day 3.1 session. So this last practical is sentimental analysis. So it classifies whether it's positive or negative. Okay. We'll do this last one. I don't have this on my side, so I'll do it from scratch. So from transformers, actually you don't need to do pipeline, no pipeline. We already have that. So sentiments classifier equals to pipeline of sentiment analysis as well as output sentiment classifier. This is the thing that we want to classify. So dear seller, I got very impressed with the fast delivery and careful packaging of my order. So great experience overall and beauty. So we try not to make spelling errors for GPT. Try not to make spelling errors and try to make it complete sentences. So like print outputs. So it tries to classify this sentiment, whether it's positive or negative. So remember our NLP workshop, I think we have gone through this. So NLP workshop, positive, negative, or neutral, right? So using pre-trained models to determine what the context of that word. So this is one of the use cases of transformers. Label positive and it's a score of 0.99. It's like 99% sure that this sentence is a positive context. So what about something negative? Okay. What about something negative? I will just copy this over. This is a negative. So let's say not the GPU. Let's say negative sentence. Dear seller, the products are really bad and I do not recommend buying from this seller. And then it tries to output that negative with a 99% sure that's negative, and so it's like 99% sure that's positive. Yeah, so this uses probabilities context. I think it's okay. Although it's a very black box for how all this works behind the scenes. Okay, we don't really go in depth into what this black box means, but we could always make inferences. So for how people who write their research papers on all this behind the scenes stuff, actually they are making inferences, they are actually making theories on how it happens. But actually, whether it's really true or not, actually, it may not be true because in the early days, right? Just want to share some information. So on the early days when they wrote their papers, right, they don't have very substantial claims to support their claims. So the papers always get rejected, right? Because it's just not enough evidence. So it's actually very hard to actually unpack this very wonderful black box. Actually, but it's very confusing black box. So totally normal if you don't get the black box. But we just cover from here and that's all. Positive, negative. Okay. So I hope in just 3 lines of code, you could already do something meaningful to our. You can even use this for your what's that called? Your websites. You deploy in Discord. Feel free to explore this on Discord on your HTML, JavaScript. Then you in the closing opening tag of script. Okay, I may not be a web developer myself, but at least I know. Okay, you can put this into scripts, run it, see how it works, tokenize, token the bot token, run it. Yeah. Other than that, that's all for day 3.1 actually. So happened that we end very early, 11:22. We will be back for a long lunch break today. So we'll be back at 1 p.m. or rather 1:10 because we want to get you will give some buffer time for students to get in. So we'll be taking a lunch break now until 1:10. Thanks everyone.